Hello all.
My name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we're going to discuss about various generation methods of your DSB-SC signal, such as your balance modulator and your ring modulator. So these are the outlines. We're going to start up with the introduction where we will going to describe whatever we have studied in our last lecture. Then we're going to discuss your DSB-SC waveform, which will be followed by the block diagram description of your balance modulator. That is how with the help of balance modulator we will going to generate your DSB-SC signal. Then we will going to discuss your ring modulator, its block diagram structure and its detail. That is how with the help of ring modulator we will going to generate your DSB-SC signal. So in our last lecture, we have studied about the basics of DSB-SC system, its power and its bandwidth requirement, along with all its mathematical detail. We have found the mathematical equation of your DSB-SC signal, such as DSB-SC signal would have been given as your AC times of MA over 2, where this MA is nothing but your modulation index, which could also be represented as your mu, times of cos of 2 pi FC plus FMT. This is signifying your upper sideband, plus cos of 2 pi Fc minus Fmt. This is signifying your lower sideband. So this is how we will going to represent this DSB-SC signal. So in this particular lecture, we will try to discuss various generation methods of your DSB-SC signal. So this particular figure is basically showing your DSB-SC waveform. This is nothing but this is showing your envelope of your DSB-SC signal. One should observe closely that here at this particular moment phase transition will going to take place. That is, here carrier is not continuous, it is basically changing its phase. From here it is not going downward, it is going just upward. That is, here we'll be having this 180-degree phase shift. This is the time domain representation of your DSB-SC waveform. This particular envelope is basically showing your over modulation case, and this is the frequency domain representation of your DSB-SC signal. That is, we will be having this upper sideband, which is shown by this green color. That is your Fc plus Fm. This is your upper sideband, and this is your lower sideband, Fc minus Fm, which is situated at your Fc minus Fm. So this blue color is basically showing the lower sideband, and we have shown this Fc signal with this dotted line since it is absent in your DSB-SC signal. So double sideband suppressed carrier signals are generated by a circuit that would have been called as your balance modulator. The name balance comes into picture just because it will going to balance out the carrier power. So the purpose of the balance modulator is to produce the sum and difference frequencies, but to cancel or balance out the carrier. That is, it will going to suppress your carrier signal and only allow to transmit two sidebands, that is your upper sideband and lower sideband. So the following two modulators can generate your DSB-SC wave, such as your balance modulator and your ring modulator. So we're going to discuss both of them one by one. So first we're going to start up with this balance modulator. So this particular figure is basically showing the block diagram of your balance modulator. Here we'll be using two AM modulators. This is your first AM modulator, or you could say your upper AM modulator, and this is your lower AM modulator. So here important point is both of these modulator will going to get the same carrier frequency generated by this your LO, and that will be equal to AC times of cos of 2 pi FCT. That is, both of these modulator will going to get this same carrier frequency, and one modulator is getting this message signal empty, and second AM modulator will going to get this message signal minus times of empty, or you could say 180-degree phase shifted version of your original message signal. So then both of these two product multiplier or your AM modulators outcome will get combined through your summer, and at the output we are getting this signal ST, which is nothing but the summation of two, that is your S1T and S2T, which is nothing but the outcome of your this upper modulator and this lower modulator respectively. So the summation of these two, that is S1T and S2T, will going to gives us your signal ST, which is nothing but your DSB-SC signal. Here one thing should be noted, that we are saying that the summation of these two signals, but the point is polarity wise this lower AM modulator signal is negative. So we are basically going to get effectively S1T minus S2T, that will be equal to your ST, which is nothing but your DSB-SC signal. So when we're going to discuss this mathematical equation, we will clear that what I'm trying to say. So the two modulators are arranged in a balanced configuration in order to suppress the carrier signal. So whole agenda is to save some power while suppressing the carrier signal, since carrier does not convey any sort of information. Hence it is called your balanced modulator since it is balancing your carrier power. Output of the upper AM modulator would have been given as S1T will be equal to AC times of 1 plus mu times of MT cos of 2 pi FCT, where this cos of 2 pi FCT is nothing but it is representing your carrier signal, and this mu is nothing but it is representing your modulation index, and AC is the peak amplitude of your carrier signal. So this is what about the output of your upper AM modulator. And similarly, the output of the lower AM modulator would have been given by this S2T, that will be equal to AC times of 1 minus mu times of MT cos of 2 pi FCT. Here this minus sign comes into picture due to minus MT only. So the summer block produces an output ST, which is the difference of S1T and S2T. So effectively what we are getting is ST is equal to AC times of 1 plus mu times of MT times of cos of 2 pi FCT minus AC times of 1 minus mu times of MT cos of 2 pi FCT. And when we're going to solve it out, then in that particular case, your AC signal, or you could say your carrier signal, will going to cancel out with each other, and we are left with this your 2 times of AC times of mu times of MT multiplied with your cos of 2 pi FCT, which is nothing but your DSB-SC signal. We can easily see that there is no separate carrier component present in this particular equation. So this is only going to contain your two sidebands, that is your upper sideband and lower sideband. So this is how, with the help of balanced modulator, we can generate our DSB-SC signal. So now we will going to discuss another mechanism or method for generating your DSB-SC signal, that is your ring modulator. A modulator in which 4 diode elements are connected in a series to form a ring around which current flows readily in one direction. Since all these 4 diodes are connected in the series of the ring, that is why the name ring comes into picture. So input and output connections are made of 4 nodal points of the ring. That's why the name ring modulator is proposed. So this particular figure is basically showing the block diagram description of ring modulator. Here we will be having 2 transformers, that is your T1 and T2. Here this T1 transformer is your audio transformer, that is it is only being functional at your lower frequencies or audio frequencies. We will be having 4 diodes D1, D2, D3 and D4. Here we are using basically center tap transformer, and we have applied this common input signal CT, your carrier signal, like this. So here we have made one assumption, that is your carrier signal magnitude or amplitude is greater than your input signal magnitude. So that switching of the diode, that is on or off situation, would have been totally dictated by this carrier signal. That is, carrier signal is responsible for making all these diodes on and off, and how this circuit will going to get functional, we will going to discuss. So let us assume that when CT would have been applied at this particular terminal, then what will going to happen to our circuitry. So obviously carrier signal is your high frequency signal. So at these carrier frequencies, your audio transformer will going to behave like your open circuitry. So this will not going to get functional. So CT will going to take the responsibility for making all these diodes on and off state. So now let us understand the working of this ring modulator. We're going to apply our message signal XT to the primary winding of our transformer T1, and we are assuming that the polarity of CT is like at terminal 1 it is positive and at terminal 2 it is negative, or you could say that at the positive cycle of your carrier signal we are assuming its operation. That is how it will going to get functional. So when CT is positive, then in that particular case your diode D1 and D2 they will only going to get conduct, and your diode D3 and D4 they will going to be your non-conducting state, or they are in your off state. So for the simplicity we have just avoided from this particular circuitry, since they will going to work as your open switch. So this is the modified structure of your ring modulator in your positive half cycle of the carrier signal. So how our circuit will going to work? So here, since this is positive, then it will going to conduct like with this particular path. Here at this particular point our signal will get bifurcated, that is one portion is going to upside and another portion is going to downside. So for this above portion your diode D1 will going to conduct, and it will going to follow this particular path to get back to this CT. Whereas for this second portion which is coming downward from here it will going to follow this particular path via D2. It will going to go through here, and this is how. So when XT signal is applied at the input, due to the induction, that signal value or potential at A will going to translated or switched at A, and the signal value or voltage at B will going to appear at this B1. Your potential at AB will going to get switched at your A1 and B1. So at this particular moment, during the positive half cycle of your carrier signal, we could say that positive xt would have been switched to this points A1 and B1, which are basically transported to this secondary coil of your transformer due to the induction, and its voltage value turns out to be your Vt. Whereas when we will going to consider second case, that is when the polarity of your carrier signal will going to get changed, then in that particular case your diode D1 and D2 will going to work as your open circuitry, or they will going to be in your reverse bias, and diode D3 and D4 will going to conduct. So in this particular situation, what will going to happen is whatever signal is appear to your A and B, that will going to further switched to this particular point B1 and A1. So how? Let us see. So this is the polarity of your carrier signal. So our signal will going to follow this particular path. Please follow this particular pointer. That is, signal will going to flow through like this, this. After this, it going to come over here. Then in this particular case, your D3 will going to conduct, and via this particular path, it will going to end up over here. Whereas since here we will be having a bifurcation of our signal, so one portion is comes down and another portion is going upwards. So this second part, which is going from here to here, so it will going to follow this particular path, that is via D4. It will going to enter into like this. So here one thing should be noted, that in this particular scenario, your voltage at particular point A will going to switched at particular point B1, and the voltage at particular point B will get switched at particular point your A1. So here the polarity would have been reversed, or you could say that we have switched basically minus times of xt at this particular moment. So here the Vt value will be equal to minus times of xt. So when we are going to pass through that particular signal through the band pass filter, we will going to get our DSB-SC signal as an output. So how? Let us understand it with some description. So working operation of the ring modulator. Assumption we had already made that your carrier signal amplitude is much greater than your message signal amplitude, that is your xt. So T1 is the audio transformer, hence it will work nearly like an open circuit at the carrier frequencies, or you could say it will only going to get functional at your lower frequencies. So CT basically controls the behavior of the diodes, which would be acting as your on and off device. So here we are assuming that we are using some ideal diodes. The complete operation would have been understand into your two cases, that is when CT value will be positive or CT value will be negative, or you could say when your carrier signal in your positive cycle and when your carrier signal is in your negative cycle. So case 1, when terminal 1 is positive and terminal 2 is negative. So this is the case when your CT is in your positive cycle. So diode D1 and D2 are forward biased as we have discussed, and diode D3 and D4 are reverse biased, or they are in off state. So only diode D1 and diode D2 will going to conduct. The voltage at point A will get switched to A1, and voltage at point B will switch to B1. So we could say that plus xt would have been switched, or we will going to get Vt as your plus xt. Whereas in case 2, when we will be having reverse polarity that we have assumed in our first case, that is terminal 1 is negative and terminal 2 is positive, then in that particular case it will basically going to make our diode D3 and D4 are in forward biased, whereas diode D1 and D2 are in reverse bias, or they are in non-conducting state. So due to this particular situation, or the conducting state of D3 and D4, the polarity of switching voltage would have been reversed. That is, the voltage at A will get transferred to your B1, and the voltage at point B will get switched to your A1. So in this particular situation, we can say that Vt value will be equal to minus times of xt, or negative polarity would have been appeared. So hence we can conclude that during positive half cycle of the CT, obviously the carrier signal we are talking about, plus xt is switched to the output, whereas during the negative half cycle, minus xt is switched. Hopefully explanation is quite clear. Hence the output of the Vt can be given as Vt is equal to xt times of xpt. So Vt is basically switching your xt signal. The polarity might get different. That is, for positive cycle of your carrier signal, plus xt would have been switched, and for negative half of your carrier signal, minus xt would have been switched. So Vt can be represented with the product of this xt and this particular pulse xpt. So what is the type of this particular pulse xpt? So xpt is a square wave as shown in figure. So this is the wave that would have been given up the characteristics of your xpt. Here the value of t naught will be equal to 1 over fc, which is nothing but your inverse of your carrier signal. So for up till this duration, we will be having positive value of xt, and in the negative half cycle, we will be having this minus times of xt. So this is basically showing your switching state. So our Vt signal would have been easily represented with the product of this xpt with your xt. That is, for positive value of the pulse, we will be having this xt as your Vt, and for negative value of pulse, we will be having this minus xt as your Vt. So it could have been simply represented with this particular thing. So the Fourier transform of xpt would have been given as 4 upon pi, only odd harmonics are there, minus 1 times of n minus 1 upon 2 upon n cos of n omega ct. So this is the Fourier transform representation of this particular rectangular pulse. Here one thing should be noted, that the peak value of this particular pulse is your unity. So it will not going to affect or alter the amplitude of your signal. So let us say if this is showing our message signal, then the output would have been represented by this particular figure. That is, for positive half cycle, we will be having diode D1 and D2. They are in on state and we are having this particular sort of waveform. And for negative half cycle, when diode D3 and D4 are conducting, we will be having this particular portion. So since this is your message signal, so obviously if we are talking about positive switching and negative switching, so this is the output that will be equal to Vt when D1 and D2 is on, and this blue color is basically showing your minus xt when D3 and D4 are present. So we will going to have got this sort of pattern as your output signal, or you could say this particular figure is basically showing the value of your Vt. So when the signal Vt is passed through the band pass filter, the output of DSB-SC signal turns out to be your st will be equal to xt times of cos of omega ct, which is nothing but your DSB-SC signal. We can easily say that there is no separate carrier component present over here. So this is how we will going to generate our DSB-SC signal with the help of this ring modulator. So we can have only DSB-SC signal present at the output, since carrier component will going to cancel each other. So hopefully you guys have get the idea about the working of your ring modulator. In case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references. Thank you very much for your patient hearing.